All right, welcome to another video, Chem with Com. We're gonna continue the molecular structure and polarity series. This is going to be the second lecture, and this is specifically electronegativity and polar covalent bonds. So electronegativity and polar covalent bonds. All right, that's a mouthful. All right, let's take a look at what we know. We know covalent bonds, and these are just called pure covalent bonds or covalent bonds. This is between two nonmetals. They are held together by covalent bonds, like the sharing of electrons, right? Oh, yeah, sorry. Sharing of electrons here. Covalent bonds are formed by atoms sharing electrons. And let's emphasize this equally, right? They share them equally, right? Me and my brother share a soda, right? We have half and half, right? It's equal. Now we're going to introduce something new called polar covalent bonds, or you can also call them polar bonds, right? Like polar bears, but polar bonds. That's what actually, yeah, we'll cover that later, but it's also between a nonmetal and nonmetal. They're held together by covalent bonds. But here's where it's different. Covalent bonds are formed by atoms sharing electrons unequally. Unequal means it's polar. All right, and we'll take a look at what all that means. All right, and let's just get something in our head, right? If you look at the Earth, right? Pole Earth has poles, right? The North Pole, and the South Pole, right? One side of the Earth is considered the North Pole or the North Hemisphere. The other side is considered the South Pole, the South Hemisphere, right? So let's just remember that when we talk about the word polar. All right, another thing we're going to need to know also is electronegativity. And this is basically the definition, is how much an atom pulls electrons toward itself. All right, that's it. So let's take a look at electronegativity of lithium and fluorine. All right, I'm just going to look at valence electrons. So let's look at valence electrons. Lithium has two energy levels, or yeah, okay. But we're only going to put electrons on the valence shell. One valence electron. Fluorine has one, two, three, four, five, six, seven valence electrons, but it has, same thing, two energy levels. I'm going to draw this a little exaggeratedly, but one, two, three, four, five, six, and seven. Again, electronegativity, how much an atom pulls electrons toward itself. So lithium has an electronegativity value of 1.0. The actual number doesn't matter a lot, right? Um, this fluorine has electronegativity value of 4.0. So fluorine has a higher electronegativity value, which means it pulls electrons really, really, really close to itself, right? And so you can see here, this is smaller. The radius is smaller because electrons are closer to the nucleus, right? It shrinks it. It shrinks it because it pulls the electrons closer. Now, what also happens is that if there are other electrons around, it's going to get pulled closer as well. So other electrons get pulled closer as well. Pulled closer as well. And this is what we're going to do here for this class. Some classes make you do these electronegativity values. What really, really is important is you know that the highest electronegativity values are on the up and to the right of the periodic table, right? So up and to the right near fluorine. Fluorine is the most electronegative thing there is. atom there is. So we're going to use fluorine as our kind of symbol. Hey, that's where we need to, that's our highest electronegativity atom is fluorine. The opposite end of the periodic table, all the way over and to the left, left and down, is going to be the lowest electronegativity, right? So we're going to use that trend to figure out what's polar, what's not. And there's going to be some mistakes in there and some kind of squishy values that aren't super exact because we're just using a trend, right? For example, it would be hard to figure out what's more electronegative, right? Carbon or sulfur because it's up and the trend is up and to the right. Well, this is carbon's up and to the left, sulfur's right and down, so it's hard to figure out that trend, right? But for the most part, we're gonna try and stick with just trends. I don't want you guys to memorize these numbers, right? So again, highest electronegativity is up and to the right, lowest electronegativity is down to the left. And electronegativity is how much an atom pulls electrons toward itself. All right, so let's take a look. Lewis structures. Again, if you need a review for Lewis structures, go back to topic 3. I think part 2 is Lewis structures. So I'm going to draw this exaggeratedly. All right, so hydrogen and hydrogen. Now, their hydrogens are identical. They have exactly the same electronegativity. Two, again, we don't really need to know the numbers right now, but for this, let's just do that. So each of those hydrogens are going to pull electrons toward itself. And they're sharing a set of electrons. But since both of them have the same electronegativity, this is equal sharing of electrons. All right, equal sharing of electrons. Let's do the same thing with chlorine, right? Chlorine and chlorine. Well, if you do the Lewis structure, it's going to look like this. Each chlorine is the same electronegativity, so it's going to, each of those chlorines are going to be pulling on those center electrons. But since they're the same strength, it's again equal sharing of electrons. I don't know why I said equaling. Equal sharing of electrons of electrons. All right. Equal sharing of electrons. The next one is HCl. Now we have two different atoms, right? H and Cl. So now what's more up and to the right of the periodic table? Chlorine is more up and to the right on the periodic table. So we're going to say that chlorine is more electronegative. See, electronegative than hydrogen, right? It's always going to be a comparison between something else, right? It's not, I don't like to use hard numbers. I like to say which one's more polar or which one's more electronegative, right? Okay. So since chlorine is holding those electrons closer to it, pulling it closer because it's more electronegative, those electrons are going to be more toward chlorine. Now, electrons have negative charge. So since the electrons are getting pulled toward chlorine, this side is going to be what's called a delta negative. That means it's a partially charged partial negative. And that's a Greek delta. So we'll say Greek delta symbol. Right? So you know it's not just some kind of gibberish. It looks like gibberish, but it's not. So since you have extra electrons on the chlorine side, you're going to be negative because those electrons are negative. Now, if you're losing some of that negative charge, that makes you positive. All right? So you have this positively charged or partially positively charged hydrogen. You have this partially negative chlorine. All right, so you have positive side, negative side. And if we look at the Earth, right, we have a north side and a south side. And this is polar. The Earth is polar. This molecule is also polar. So these are the delta symbols or the partial charges. So we'll say partial charges or delta symbols. We also have what's called a dipole moment, because if you look at this entire molecule, right, the electrons are getting pulled toward chlorine. Right? Electrons are getting pulled toward chlorine. And you're going to draw a little plus here. This is called a dipole moment. Molecule, it has a positive side and a negative side. Not a full positive or a full negative. They're partially positive, partially negative, because they didn't lose electrons, right? They're still sharing. But since it has more electron density near the chlorine, that's going to be a slightly more negative. And since it has a partial, it's losing some electrons on the hydrogen side, not losing completely, but away from the hydrogen, that's going to be partially positive. And because we have a positive side and a negative side, right, that's going to be a polar molecule. And so it has a dipole moment. All right, let's look at this HCl here. This is kind of a better annotation here. Again, these are symbols for partial positive right here. This is a symbol for partial negative. Those are, again, Greek delta signs. So you're going to have this green, how dark it is, how dense the electrons are there. And so you can see on the right side, there is much more electron density for the chlorine. On the hydrogen, it's a little lighter green. On the left side, it's very white. That's going to give you the sign that that's where it's a kind of partially positive. And again, this is what's called the polarity vector or the dipole moment. And we indicate the positive side by having that little cross there, right? And the arrow is pointing toward the location of higher electron density. All right, so let's practice a few of these. All right, so you can measure the electronegativity difference between atoms. And this isn't, I don't like using this a lot, but it's good in the beginning to learn. So we're going to look at the difference between 3.0 and 2.1. So one way to do it is you take the electronegativity of the first thing minus the electronegativity of the second thing, and you do what's called the absolute values, and that's your electronegativity difference. That's a triangle. It's another delta sign, but it means difference of. Or you could say larger electronegativity minus smaller electronegativity equals the electronegativity difference, right? So we'll say difference of electronegativity. Difference in electronegativity, right? And so you're doing that calculation and you see that, hey, the electronegativity difference is less than 0.4. That's a purely covalent bond. If it's greater than 1.8, it is an ionic bond. Basically, what happens is electronegativity difference is so big, the atom, the more electronegative atom, just takes that electron because it pulled it so tight to itself, it doesn't, it just gets the whole electron, right? Here's what's a little kind of finicky is if it's between 0.4 and 1.8, that's considered a polar covalent bond. And we're just going to call it polar. We're going to call this one covalent so that we can use less vocabulary, right? So let's just say this is covalent, this is polar. All right, so again, if you do the electronegativity difference, sorry, I never did the math there. It's 3.0 minus 2.1, that's 0.9. Well, 0.9 is between 0.4 and 1.8, right? So that's going to be a polar bond. Again, we're talking about bonds only here. So bonds, this is a polar bond. All right, let's use these numbers and take a look. And let's check our learning here. They're saying they want an SiO bond, SiC bond, a CH bond, and a CC bond, right? And let's look at the electronegativity values. Let's start at the bottom. This is going to be 2.5 minus 2.5. That's going to be 0. So that's going to be covalent. And maybe in brackets, I'll put pure so that we know what we're talking about, right? All right, let's do another one. Let's do carbon and hydrogen. Carbon and hydrogen is 2.5 minus 2.1. That's going to be 0.4. So what is that? That's going to be right on the cusp. It's right between 0.4, or sorry, covalent and polar. It's right on the line here. So this one's kind of hard to tell, but let's just go exactly what the chart says. And it's actually 0.4. So we're going to call this a polar bond. But maybe in parentheses, we'll say weakly polar. Right? Because it's right on that cusp. All right, let's do another one. Si and O. Oh, sorry. Let's do Si and O. Let's do this top one here. So it's going to be, I'm going to label these now. Maybe I should have been doing that. 2.5, 2.5. This is 2.5, 2.1. All right. Silicon is 1.8. O is 3.5. Let's do 3.5 minus 1.8. That's going to be 1.7. So if you look that up, right, it's going to be polar because it's between 0.4 and 1.8. So we're going to say it's polar. All right, let's do another one. Silicon is 1.8. Carbon is 2.5. So we're going to do 2.5 minus 1.8. This is going to be now 0.7. That's also going to be polar. All right, now let's look at these values here. And it says, arrange the bonds in order of increasing polarity and designate the positive and negative atoms using these delta symbols. I'm going to do it in a different color just so we can take a look here so you can see it better. All right, here this is not polar, so we're not going to have those delta symbols. Not polar. No, what do they call it? I'm going to change the vocabulary a little bit, but they don't really mention this, but no, um, sorry, no partial. No partial, positive, or negative sides to the molecule, right? Because they're sharing electrons equally. There's no positive side, no negative side because they're the same. All right. This is going to be slightly positive because it's a little weaker, and this is going to be slightly negative. This side here is slightly negative. This is slightly positive, right? Because the 2.5 is bigger than the 1.8. The oxygen is definitely going to be slightly negative. The silicon is going to be slightly positive. Okay, so let's also draw polarity vectors or dipole moments, right? We're going to draw the arrow going toward the negative side. And we're going to put that little plus on that side near the positive side. All right, the arrow again points toward where those electrons are going with the little plus on the positive side. This one, there is none. All right, so now again, let's go back to looking at these values. We're going to go from increasing polarity. So increasing equals small to large. So we're going to say the carbon is first. The carbon hydrogen is second because that's 0.4. Then the silicon carbon bond, and then the silicon oxygen bond, right? And we can just reaffirm this. We'll say small, let's see, we'll see. We'll say least polar, and we'll over here it's going to be most polar. All right, that's it for the video. I will catch you next time. Thank you.